Hello, everybody. My name is Singbom Hong. I'm a professor in the Department of Material Science and Engineering at KAIST in Korea. Today, I'm going to talk about screening mechanisms at polar oxide heterointerfaces. And before presenting my talk, I'd like to briefly introduce our lab. Our lab is called Materials Imaging and Integration. And as you can see from our homepage, my is family. And I'd like to thank all the members in my group to help me prepare the slides. Let me first begin with the summary of my talk. So if you decide to do so, you can just listen to this part and leave. So the 3 bullet points summary is given in this slide. And the first is that the interfaces of polar oxide heterostructures can display properties unique from the oxides they border, as they require screening from either internal or external sources of charges. I will specify what I mean by internal or external sources of charges in the following slides. Second, the screening mechanism depends on a variety of factors, including the band structure at the interface, the presence of point defects, or adsorbates like hydroxyl or protons, whether or not the oxide is ferroelectric, and whether or not an external field is applied. And ferroelectric is a term that is well defined in the textbook, where spontaneous polarization, which is the dipole moment per unit volume, can be switched by external electric field to equivalent states in terms of energy. Third, the ability to manipulate electron transfer and absorption/desorption at polar surfaces may be the key to developing next-generation electronics, tailored and tunable catalysts, and energy technologies, to name a few. So these 3 bullet points will be the summary of my talk. So for those who are not familiar with the terminologies, I'd like to briefly introduce them on this slide. So here you can see the oxide, which is the green part in the slide, so the rectangle there, and you have top layer and bottom layer. And this oxide layer can be ferroelectric or not, and if it is ferroelectric, it will have spontaneous polarization that can be switched. If not, then it can either have induced polarization if it is centrosymmetric, or if it is metallized, then it would be hard to have a unique polarization that stands out of this layer. In the vicinity of the oxide, we'll put top layer, which can be metal, oxide, or semiconductor, and bottom layer, which can also be metal, oxide, or semiconductor. And as you can do, think about the possible combination. We can have sandwich structure, bare film, or freestanding membrane. And we will think about place of source for the screening. So that could be internal if it is supplied from inside. If it is supplied outside the oxide, it will be external screening. And depending on the identity of source, it can be intrinsic, which is from the native components of the oxide, or extrinsic if it is foreign impurities or neighboring atoms or ions that are supplying the screening charge. So the contenders in this picture will be electron hole versus ions such as adsorbate, defects, and space charge. All of the slides are based on the review paper that I, together with Serge Nachmanson and Dylan Fung, wrote in Reports on Progress in Physics in 2016. In addition, I also excerpted some slides from my own Coursera course that is online in coursera.org, and I will specify wherever I excerpted my own slides from the course. In fact, this slide is from the Coursera course and based on lectures on Physics Volume 2 written by Richard Feynman. So before going further, let's revisit why we are interested in the magnitude and direction of electrical forces. As you know from classical mechanics, the destiny of a particle depends on the force acting on it and the path that is available to that particle. In material science terminology, we call that thermodynamics and kinetics. So in terms of thermodynamics, driving force is very important because this will give the impetus to change the position and velocity of the particle of interest, which will either participate in making materials or breaking materials. So let's think about this hypothetical situation. For example, we all know we have plus and minus charge in the world, but we don't feel it. And the reason why we don't feel it is because macroscopically the electric field coming out of those charges are averaged out to be zero. And in other words, the number of plus and number of minus charges are equal. What if it is 1% off? And we can calculate using Coulomb equation and see that even 1% imbalance of protons and electrons will result in enormous force. For example, you can even lift the entire Earth by ripping off 1% of electrons from each of person. Now, that is not the case when we scale down to atomic scale, right? As you can see from the rock salt structure, you know sodium and chlorine ions are alternating in each site. And if you cut the salt in 111 direction, you can see that in one plane you all have plus charge, in other plane you have all minus charges. So if electric force is so enormous, then you can imagine they will not hold it together. But because of the superposition of repulsive and attractive force, you can calculate the Madeline's constant that will roughly give you the bonding force between these planes. And still, you can understand the force is enormous. So if you play with these planes, for example, if you remove one of the plane, you immediately set up an internal electric field that will destabilize the matter. And that is related to the screening process of oxide surfaces. So let's start with the classification of polarity screening mechanisms and think about origin of screening charge. So when I say origin of screening charge, in other words, it means where do they come from? Where do the screening charge come from? So as I told you, we can either have intrinsic charge carriers or extrinsic charge carriers. Intrinsic charge carriers are electrons and or holes provided by the dielectric itself or its integral component. So they are native. Whereas extrinsic charge carriers are electrons and or holes donated by neutral or charge point defects like vacancies and interstitials, impurities or foreign atoms present inside the dielectric, and electrons and or holes provided by the neighboring layers in the superlattices. Now let's think about the place of screening. So where do these screening charges work? Where is the what is their workplace, right? So then we can then classify the workplace into internal screening and external screening. When we say internal screening, electronic carriers or charge point defects like vacancies, interstitials, they are present within the dielectric. And the carrier and ionic species concentration change leads to change in local polarization. In the meantime, for external screening, conductive electrons in metallic electrodes absorb foreign charged species like hydroxyl, hydrocarbons, and so on, or mobile electronic and ionic species supplied from the environment or external circuitry can be the candidates. And in an idealized defect-free material, polarization distribution is uniform and changed abruptly at the interface because they are screening the electric field, so stabilizing the polarization inside. And by the way, these two screening mechanisms can compete. They're not exclusive. They can compete, and it depends on many, many factors. So now let's move on to the surface polarity. So surface is the interface between your oxide layer and the ambient air, right? And we can categorize the surface polarity into two, namely nonpolar surfaces, where surface charge density defined by sigma sub s is equal to 0. So charge is compensated by construction and no further surface modification is needed. So by the design of the atoms or ions that make the material will help themselves, right? Whereas for polar surfaces, sigma sub s is non-zero. So because it's non-zero, it leads to the divergence of the slab surface energy. So the more slab you add up, you will have larger energy piled up. And at some point, it will spill through the band gap because it cannot sustain that kind of energy. And it needs to be compensated by surface charge density sigma sub c. So the equation sigma sub s plus sigma sub c equals 0 will be very important. So this slide shows an example how we can choose the slab unit cell to make non-zero or zero dipole moments inside the unit cell. So you may wonder, is it really the choice of the slab that makes surface polar or non-polar? The answer is no. It is to show you for semi-infinite slab to have a repeating units with different choice, and that different choice will result in a very small change on the surface that will also change the nature of the surface. Okay, so take a look at the picture below, and the blue rectangles are positive ions and red dots, they are electrons. So for non-zero dipole moment case, if you look at how we slap the unit cell, how we slice the unit cell, you can see the summation of plus and minus charge is 0. And because of our choice, we leave the surface electron that is half filled isolated and dangling, and therefore we have non-zero dipole moment, we have non-zero surface charge. However, if you look into the slab unit cell choice for zero dipole moment, you see that we slice through the positive ions so that, again, inside the unit cell it is 0. However, even for the surface isolated electrons, if you take into account that it is half of the electrons for a unit cell, that makes a whole, and therefore you will see the surface charge density is 0, and therefore the dipole moment is 0 as well. So with that in mind, let's move on to surface polarity compensation. So there are basically two scenarios. The first scenario is modification of the number of the surface ions. So this is formation of non-stoichiometric surfaces, because stoichiometric 1 may have polarity. So we need to change the ratio of plus and minus so that we can compensate the surface. In that case, we have two mechanisms in competition. The first one, internal screening, where native species deliver the compensating charge, creating surfaces that can contain partial or incomplete atomic layers. And at the same time, we can have external screening, where adsorbates or impurities are captured by the surfaces from the ambient. So let me give you a specific example, which is excerpted from one of the chapters that I edited, one of the book chapters that I edited long time ago. As you can see, it's from Professor Rainer Wasser's group, who contributed to nanoscale phenomena in ferroelectric thin films, which was published in 2004. And there, they describe the process of self-polarization in lead titanate bulk crystal. And as you can see, there is a surface reconstruction going on, as you can see from the SIMS profile, where we have different stoichiometric layer when compared between surface and bulk. So in comparison to bulk, the surface layer is non-stoichiometric, and that is pronounced by the ratio of the lead oxide on top of it, and is also confirmed by the X-ray diffraction pattern peaks that you see on the lower side. Another interesting example comes from my own work with my postdoc, who I co-advised with Andreas Reloff, is about the external screening. So for periodically poled lithium niobate, you can see that adsorbates or impurities like hydroxyl or hydronium ions are captured by the surfaces from the ambient. And using charge gradient microscopy and Kelvin probe force microscopy and electrostatic force microscopy, we can investigate the adsorption process and desorption process by the atomic force microscopy tip, and also how they're being recovered as a function of time because of the thermal energy provided and the electric field, stray field, coming out of these crystals. And now let's move on to the second scenario of surface polarity compensation. So the second scenario is about electron charge transfer into or out of the surface region. And in this case, substantial modification in the structure and filling of the surface electron bands will occur. And we will have three different types of modifications. The first one is charge transfer type, especially for wide bandgap oxide, where surface cations trappings excess electrons, while surface anions trap excess holes. So surface cations can trap excess electrons, while surface anions can trap excess holes. Now for Mott-Hubbard type narrow bandgap oxide, multi or monovalent surface cations can trap either electrons or holes. And in case of monovalent ions or oxygens, excess electrons or holes in the surface region can lead to partial filling or depletion or surface conduction or valence band, which will lead to surface metallization. And because of that, we will have Fermi level pinning. And we can also think of special cases like weakly polar 001 perovskite surfaces, where no serious modification of band structure or band filling happen. Surfaces of ferroelectrics, where we can form domains, stripe domains, or AC domains, vortex, closure domains, or surface adsorbates or surface restructuring, as I showed you 2 slides before, or finite size effects in ultra-thin films, in which case uncompensated slab can be stable. So we can have uncompensated polar ordering. So then let's dig into this interface polarity compensation, which is similar in nature if compared with surface polarity compensation. Now, instead of having air as the substance in the vicinity of our oxide boundary, we have another oxide or another class of materials like metals or semiconductors, and we have to think of the charge that will be either accumulated or depleted at that interface. And with this equation, sigma sub I is equal to the integral from minus ZA to ZB of rho tilde of Z dZ is the equation we can use to evaluate the surface charge density. Now for non-polar surfaces, obviously sigma sub I should be 0. So by joining either two non-polar surfaces where sigma sub A and sigma sub B are all 0, or two polar surfaces with equal but opposite charge, like sigma A is equal to minus sigma B. In those cases, we will have non-polar surfaces. However, if sigma sub I is not equal to 0, which is the case with one or both of the joined surfaces are polar, then we can have three types of scenarios. The first one being electronic charge transfer in and out of the interfacial region with partial or full filling or depletion of the interfacial electronic states. Or we can have modification of the interfacial region composition / stoichiometry, which can either be intrinsic or extrinsic. Or we can have diffusion / segregation of other charged species within the interfacial region, which is usually extrinsic. So before further digging into some experimental results or details of this interface polarity compensation, let's think about the process to compute Schottky barrier heights by density functional theory, which can predict the type of interface as well as the charge density if we put two different slabs of oxides together. So we first have to evaluate the band structure for the bulk metal to determine its Fermi level, and then we have to evaluate the band structure for the bulk dielectric, determine its energy level of valence band maximum and energy level of conduction band minimum. And then the third step is to evaluate the electrostatic potential lineup between the metal and the dielectric in a model that includes both materials forming an interface with each other. And energy levels are obtained with respect to 0 of its own electrostatic Hartree potential, V sub h of r. And this equation is a typical equation which you learn from electrostatics. So let's take a look at a simple example to compute Schottky barrier heights using density functional theory. So in this slide, I brought up an example of SRO, PTO SRO nanojunction or sandwich. And you can see that DFT usually underestimate the band gap, and it becomes especially problematic when this underestimation results in the change of the nature of the contact. For example, changing the Schottky barrier to ohmic, then it becomes a huge problem. However, if it doesn't, then still we can use it with that underestimation in mind. So you can see in this case that even though the E sub gap calculated by DFT is smaller than the real E sub gap, you can still see the Schottky barrier height calculated by DFT, phi sub E DFT, is a positive value. So you can still maintain the Schottky barrier between the SRO and PTO layer. And as we just mentioned, the third step where we align the electrostatic potential level with Hartree potential for each layer, you can see we do average not only on planar direction, but we also do smoothing because there are big oscillation even inside the unit cell, which makes the calculation complicated. And you can see with these numbers crunched in, you will be able to align the levels and you will be able to calculate the barrier heights at the junction. Now, the next slide shows you a further development of this SRO-PTO SRO nanojunction. In the former slide, you saw it was non-polar, but here we also included polar cases where you develop an internal electric field, as you can see, and this will be depolarization field, which is in the opposite direction to the spontaneous polarization that we set up in the slab. And as you can see, the plane average raw potential is oscillating up and down even within the unit cell. So with nano smoothing, it is easier to grasp the macroscopic potential variation. And you can do some sanity checks that are well described in the review paper. So with that in mind, let's take a look at the real world examples and compare that with the DFT calculation. So for example, if you think about SRO and PTO slab put into contact and form a junction, and because of that, we were able to see in polar case and relaxed case or non-polar case how the polarization will be different inside the slab. However, if you take a look at the polar case, well, polarization is pointing from SRO to the air, the top layer. It predicts that we will have up polarization. And indeed, if you look at two different journal papers that we published, one in Nanoletters and the other in APL on SRO-PTO epitextually grown film, you can see indeed the as grown state will favor up polarization as confirmed by either PFM, which is piezo response force microscopy, or Kelvin probe force microscopy, or either scanning resistive probe microscopy. So now let's move on to the aspects of point defects. So up to now, and even with DFT, we thought about idealized defect-free slab and how the stoichiometry will be destroyed by moving of the ions inside or attachment of foreign impurities or adsorbates from the ambient. However, we cannot leave out point defects into this screening mechanism because it's so important. And from this slide on, we will think about the interaction between point defects and polar surfaces slash interfaces. And besides, at non-zero temperature, we learned from thermodynamics or even physical ceramics, for example, point defects are energetically favorable due to the gain in configurational entropy. And the concentration of point defects depend exponentially on their enthalpy of formation. In other words, if it is easily formed, then the concentration will explode. And as you can see, it is easier to form Schottky disorder in STO rather than Frankel disorder. And Schottky disorder can be subcategorized to strontium partial Schottky disorder and titanium partial Schottky disorder. And we can also think about electronics disorder. And on top of that, we need to think about reduction and oxidation equation into the picture. So let's think about defect energetics in STO. And you can see the Turner diagram where this is isotherm, so it means on this plane the temperature is constant, and among many points on this Turner diagram we will pick 2 points, A and F, where A is in oxidizing condition and F is in reducing condition. And from here what you can also see is the vacancies will change their energy inside the band diagram as they get ionized. So for example, if oxygen gets ionized from 0 to +2, the level, the energy level will decrease, right? On the other hand, for strontium and titanium vacancies, if they got ionized from 0 to say -2 or -4, the level will increase. And that is understood in terms of the orbitals that are influencing the energetics of each point defects. And also we can understand that it also depends, the ionizing of vacancies also depends on the character of STO, whether it's N-type or P-type, or intrinsic, as you can see on the left, no, right lower panel. It also depends on the environment, whether it's oxidizing condition or reducing condition. For those who are really interested in more details about this defect, energetics are encouraged to read the review paper we wrote into 2016. And further down the road, we have to think about electronic screening in a point defect-free ABO3. So we started with the claim that point defect is very important, but in order to delve into that, we can also always think about point defect free situation and see if we can have sufficient screening. So for example, positively charged AO surfaces are screened by electrons, and therefore on the right hand side graph, we need to have negative delta Q, which is the case on the right side, and negatively charged BO2 surfaces are screened by holes where we have positive delta Q, as indicated on the left blue arrow. And here we have three exemplary oxides, the top one being LAO, the middle one being STO, and the lower one being LMO. And you can see these three oxides are different. For example, for LAO, ionic polarization significantly reduces the polar field. In the meantime, for STO, and if you compare the numbers on the axis, y-axis, it is even smaller, and so it's weakly polar. So surface bond breaking may be enough and leads to redistribution of electrons. In the meantime, for LMO, mangan can be very flexible, so even LMO has relatively strong surface polarity, it undergoes charge doping with manganese ion, so then you can see it is well screened. Now with that in mind, let's take a look at micro/macroscopic electrostatic potential in ABO3. So you can see in case of LAO, macroscopic electric field for asymmetric slab. Asymmetric slab is stoichiometric slab, if you think about it, AO, BO2, AO, BO2. So if you have, let's say, 16 layer to match the stoichiometry of the bulk, then you see the top surface is AO and bottom surface is BO2, so you have a symmetry. So in that case, you have a charge transfer from bottom to top, and you are setting up ionic polarization. However, as you can see from this calculation, you still have electric field set up, which may destabilize the slabs overall. And this was the initial model for 2D electron gas when we put LAO and STO together at the interface. And you can also see for STO, surface stays near the valence band maximum, which is on the right side. It's less hybridized O2p orbitals, and therefore you can see, even though there's no macroscopic E field, the potential level is going down, and that can stabilize cation vacancies. And if you look at LMO, charge doping can screen each type of interface. So no matter what type of layer you have, asymmetry or symmetry, all the case, will have the same potential distribution, which is amazing. And this is due to the facile redox behavior of mangan. So let's move on to electronic and point defect screening in ABO3 with the three examples we just mentioned in the previous slides. So we can understand that polar AO surfaces, due to the electrostatics involved, attract the cation vacancies and repel oxygen vacancies. In the meantime, polar BO2 surfaces will attract oxygen vacancies and repel the cation vacancies. This is the general rule. However, if you look at LAO, it is not that simple. Even for the yellow box, you can see oxygen vacancies are welcome throughout the layer, not only on the surface, throughout the layer. And for the AO surface layer termination, the cation vacancies are not repelled. It is neither attracted, it's weakly attracted, but not repelled. So that's very peculiar. For SU and LMO, it is as stated generally. So you can expect on the surface terminating with BO2, you have more attraction of oxygen vacancies. for the layer terminated by AO, you will have more cation vacancies attracted, segregated there. So that's a no-brainer. Now, so let's take a look at the LAO cases, which was peculiar, and take a look at take a look at it from a different perspective. So here you can see the DOS level, the DOS density of states as a function of the energy level on the right side for bulk LAO and LAO surface and ALO2 surface termination. And you see the acceptor states created in ALO2 rich slab lead to hole doping. You see that. You see the Fermi level there, and you can see how it's hole doped. And with introduction of oxygen vacancies that are ionized, the liberated electrons can partially fill the lower energy surface states, and therefore it leaves the vacancy states empty and improve oxygen vacancy stability when compared to stoichiometric LAO. Now, further down the road, we will briefly discuss about the effect of oxygen vacancies on the electrostatic potential in AbO3. So for the three cases we just discussed, LAO, STO, and LMO, you can see the defect-free profile is marked in blue. It is significantly altered in the case of LAO, helping to remove the macroscopic field. So if I put oxygen vacancies on the right-hand side, you see the internal electric field disappears. However, smaller changes are seen for STO and even less for LMO, illustrating the relative importance of electronic screening in these less ionic systems. So now let's move on to the screening effects as a function of thickness. So in this talk, I'm not going to deal with low thickness regime, but I'm going to just brush over these regimes. So for high thickness regime, the surface/interface energy diverse and screening is required, either at surfaces or at buried interfaces or both. For low thickness regime, the energies for the uncompensated surfaces may be similar to those for compensated ones. So you probably do not need screening. And these apply to superlattices or ultra-thin films, which I will not cover today. So let's take a look at the high thickness regime and start with surface compensation and with the water absorption to start with. So water absorption on oxide surface has been studied for many decades, and still it's being studied. And as you can see from Morimoto's study, the portions of physisorbed and chemisorbed water molecules on titanium dioxide and iron oxide surfaces are 1 to 2, indicating that a water molecule is absorbed on two hydroxyl groups through hydrogen bonding. And as you can see, even heating up to like 600 degrees Celsius, you still may have a water layer on top of your oxide. Now, another example of water absorption can be found on strontium titanium surfaces. And from Everett Stoff group's paper, water has been predicted to absorb dissociatively on SRO terminations, whereas absorb molecularly on titanium oxide terminations. And this has an impact on the screening of our oxide surfaces. Another interesting work on water desorption from barium titanium surfaces, and Wang et al. Found desorption is a second order action, chemical reaction, and its coverage independent. As you can see, the slope of this curve on the right hand side graph shows the desorption energy, which is 1.28 electron volt. Now we will also think about water absorption on barium titanium surfaces and its influence on polarization. So how do they interact with each other, and how did they change the screening landscape? And you can see two important things here. So either oxygen vacancies or surface titanium can serve as the place where the hydroxyl or the protons resides upon the adsorption of water layer on top of barium titanate. So for example, for oxygen vacancies, we can expect dissociative adsorption near an oxygen vacancies that fills the vacancy with an OH group and transfer the proton to a nearby surface oxygen. Whereas surface titanium serves as an active site such that a hydroxyl group bonds directly to titanium, and 1/5 of all surface titanium atoms form bonds with OH groups, placing an adjacent proton on a nearby surface oxygen. So the graph below this bullet shows that with the OH minus coverage, the Pendry-R factor first slightly decreases and increases. That shows that the bonding to OH minus leads to stronger uppolarization at the surface of barium titanate. Another interesting example comes from Argonne National Lab. My colleague Dylan Fong and his collaborators, and Matthew Hyland and Brian Stevenson, they worked on this surface screening on lead titanate as a function of temperature and oxygen partial pressure. As you can see from the right graph, under oxidizing conditions, the PTO, SRO, STO slabs favors up polarization monodomain state, while for under reducing conditions, it polarizes downward, albeit relatively slowly, as it depends on positively charged species like oxygen vacancies forming and settling at the surface. And another interesting area is the white region below the curve, below the critical transition, when neither positive nor negative charge can compensate the surface, it exhibits a suppressed TC and becomes ferroelectric in the form of 180 degrees stripe domains. And as you can see, it also changed with the thickness. And thickness has to do with the strain. So strain can be another knob to change the dynamics of this screening phenomenon. Another interesting aspect is that the humidity affects the surface screening of ferroelectric oxide. And this is a chemical equation where you can see the up polarization ties with OH minus and down polarization ties with proton, and they can be related through this chemical reaction equation where the water added to the positive polarization can reduce the surface and change the polarization, right, to minus polarization. So with this in mind, we can think that to keep local electron neutrality during ferroelectric switching or perturbation of screening charge, the switching process, charge injection, or charge collection is coupled with a surface electrochemical process. And one example, wonderful example, is from Scher's group in Russia, where you can see lithium niobate single crystals, and they applied positive voltage to the tip to form a downward polarization, but they changed the situation on the surface by different cleaning process where they clean by DI water. You see the polar domain has the largest domain radius, while for plasma etching or acetone treatment, you see that domain is smaller. So obviously it means with water, the minus polarization attached with hydrogen is more favorable, and that is that can be understood from the chemical equation that we just discussed with the equation above. So the accommodation of screening charge requires the lateral transport across the surface, adsorption by the AFM tip, or ionic emission from the surface, and this can be studied both by DFT and other chemical tools as well as AFM. So with this knowledge, we can then think of interesting devices, and one example is ferroelectric field effect transistors. Polarization screening at a buried interface can influence the charge transport of the underlying bottom layer by changing its carrier density, and therefore in 1957 Russ has patented which I think is expired because it's very long time ago. But still, you can see NPN uh, standard transistor, uh, and you have ferroelectric on top of it to modulate the transconductance. And this concept was further developed by Matthews, as you can see in the slide, using epitextually grown LAO, LCMO, and PZT. And then people are now working on negative capacitance to even further the idea to have very low power electronics. So you can see the old concept now developing into a fancy new modern technology based on the screening phenomena that we just discussed throughout my talk today. So let me summarize my talk. So again, the interfaces of polar oxide heterostructures can display properties unique from the oxides they border, as they require screening from either internal or external sources of charges. Second, the screening mechanism depends on a variety of factors, including the band structure at the interface, the presence of point defects or acerbates, whether or not the oxide is ferroelectric, and whether or not an external field is applied. Third, the ability to manipulate electron transfer and absorption/desorption at polar surfaces may be the key to developing next-generation electronics, tailored and tunable catalysts, and energy technologies. With that, I'd like to acknowledge my colleagues Dylan Fong and Serge Nachmanson for most of the parts working together in the review paper, and the funding agencies that funded our review paper, as well as the funding agency at KAIST and in Korea that funded my efforts time to prepare these slides and develop the discussions in this talk. With that, I'd like to thank you and have a nice day. Bye bye.